Hi everyone, let's start. How's it going? Morning. Yeah, so just as an announcement, the office hours, TA's office hours used to be in person, but they're going to be moved to online starting tomorrow. So that will be permanent moving forward. In general, like, do people have strong feelings about in-person versus online office hours? Yes, please. Okay. Um, is the Monday in-person office hours enough, or should we reevaluate um, another one? Oh, okay. Uh, now that you know that they exist, would that be enough? Okay, thank you. Perfect. Yeah, it's at the same time. It's just on Mondays rather than Tuesdays. Yeah. Okay. It would is the Monday one okay? Okay, sure. Yeah. If anybody has any issues, please let me know. Yes. I have no idea where he will be doing it from. The room is still reserved. Like we have a hoteling room in Klaus, so they were there before. He may still sit there and do them. I have no idea, but he could also be elsewhere. I can ask. Um, but they're not going to be like hybrid. Um, like it's too hard to do in-person office hours and online office hours. So it's going to be either one or the other. Whether he's physically in that room, I'm not sure. Um, I can ask. But yes. Other questions? Okay, thank you. Great. So today we're doing dense matrix algorithms, but really quick. Somebody on Ed asked a really good question about parallel quicksort, so I want to update a little bit. So they asked previously this term was tau log p, uh, and they asked like, well, why isn't it tau log squared p? Because if you just ignore all the other steps for a second and just look at the broadcast. Okay. The first step of the quicksort is that somebody has to pick a pivot and broadcast it to everyone. And even if everybody did random number generation, so you don't have to do this broadcast, you still have to do it. You still have to do some kind of prefix sum to figure out like where everybody's partition starts. And that is going to take tau. That's going to take log p times tau plus mu for the first level of the recursion. And then assuming that you split it perfectly in half, that p is going to turn into p over 2 in the second level, and then p over 4 in the third level, and so on like that. And so actually the summation follows this, which is tau plus mu quantity times the summation 0 up to log p of log p over 2i, because the number of processors, like the groups are getting split in half every time, but the groups are still going in parallel, so that's why it's divided by over 2 to the I. And you can see that like log, it's like division is subtraction. So it's like, this is like log p minus 2 to the I, or this is like log p minus log 2 to the I. And so sum of 0 up to log p of log p is log p squared, log squared p. And then this minus thing is not log squared p. So that is not compensated. This is like p. Like sum of numbers 2 to the I up to log p is p. So log squared p minus p is order log squared p. So that is where this is coming from. And then the mu goes away because that is smaller than this. But it's like asymptotics. So does that make sense? Other questions? So I updated the slide in the previous slide deck as well. Yeah. You don't have to derive this on the exam or anything or on the homeworks. It's just for correctness. All right. So if there are no questions about that, we're going to do dense matrix algorithms. All right. So just to recap, these are the communication primitives that we're going to be using. Broadcast, reduce, all reduce, and scan. Those can, if you have a message size m, which is like the width of the operation that you're doing, it's going to take tau log p plus mu m log p. Reminder, tau is the latency and mu is the bandwidth. And yeah, in most cases, m is like, in the previous cases that we've been doing, mostly m is like 1, usually, but sometimes it's not. Like, for example, when you have to, like in the quicksort, when you have to reshuffle everybody, m would not be 1. M would be whatever it was to reshuffle everybody. Ideally even, but not necessarily. And then more complicated is gather, I'll gather, and scatter. And that's going to take tau log p plus mu mp. So the only difference is that this was a log p and this is a p. And then all to all, there are 2 kinds depending on what kind of permutation you have. So this is recap from previous lecture. And the only reason that I do this is like we're going to use the primitives to show bounds later. So we can remind ourselves of the primitives. Okay. Yes.
Why are we introducing M now?
Why are we? M was there before. Too.
Yesterday before, or when we introduced it before?
Like when we introduced these before. Like so even so for example, like if you want to broadcast something, it doesn't have to be one element. It could be M elements.
Was it like a different variable?
I don't think so. Yeah, maybe I can check the previous slide. I thought it was there before, but yeah. In the cases, but in most of the cases that we have been doing, M is 1, so it just went away. But for full generality, there is a message size there. Okay, so matrix algorithms. So today we're doing dense matrix algorithms, and then following we will do sparse matrix algorithms later. And dense matrix algorithms are nice because they have regular structure. So remember, like we talked about regular and irregular algorithms, where regular algorithms have a nice uniform structure and everybody has the same amount of work to do. And in irregular algorithms, there's uneven work. And so like you are more concerned about load balancing and one processor getting more of the work, so it's holding up everyone else. And another really nice thing, because it has regular structure, is that you can do upfront static partitioning of the computation. And that is going to give you a even distribution of the work. Because like suppose your problem was uneven, then if you cut it up, just like for example by rows up front, you may not get a perfect load balance. Like say some of the rows had a lot more elements than some of the other rows, and if you just distributed them all like that, then it may not give you the most efficient balancing. But this will with simple static partitioning schemes. And usually you compute the computation, or you partition the computation based on the data. So the most simple ones, like you would cut it up by rows, and then you have like input, you have like an input matrix, you have an output something, either vector or matrix, and then you have maybe some intermediate sums or something. And those are all just cut up on the processors. And usually there are many partitioning algorithms that you could use. Some that we will do today are 1D and 2D. There's also cyclic and block cyclic. Cyclic is like if you have P processors and N elements, it'd be like 1 up to P, and then you start over again. So like P plus 1 up to 2P, and so on like that, like in a loop. Yeah, and we were talking about embeddings last time. One of the reasons that we're interested in embeddings is that it is often nice to think about the algorithms on a 2D mesh. Like it's natural to, you have a 2D matrix, you cut it up into blocks, and then you put the blocks on the processors. Even if you don't necessarily have an underlying actual 2D mesh, it may be nice to describe the algorithm for a 2D mesh, and then you use embeddings to convert the algorithms into like hypercubic permutations. Okay, so first we will do matrix vector multiply. Okay, so for matrix vector multiply, you have an n by n matrix, n by n, and then you're multiplying by n by 1 vector, so like n by 1. And you get an n by 1 result vector out, because you take like the outer dimensions. And so the serial time complexity is n squared multiplications and additions. Like the first, to get that first output element of C or of Y, you do this, you do like the inner product, this one times this one, and you get one single element. To get the second element, you do the second row and still the entire column, or this entire vector. So you're going over this vector n times, but you're only going over the matrix once. And so that is n squared multiplications and additions. Does that make sense? And you can see that all the rows are independent. Like everybody needs, so if you have different processors, everybody needs the vector because like the entire row gets multiplied by the entire vector, but not everybody needs all the rows. Like you could, if you had, for example, n, if you had p equals to n processors, you could just put one row on every processor, and then everybody would just do one element of the output. And that would be pretty simple. Okay, and that is called 1D partitioning, which is like the most simple parallel partitioning scheme. You split up the matrix into block rows with at least one element on each processor. So like the case I was talking about is when p equals to n, which is you just put one row per processor, and somehow everybody needs to get the vector x as well. But if you have p less than n, then you just simply put a few rows on each processor, like n over p rows on each processor. And then everybody still needs, you still need just the vector, and then you do like your rows times the vector, and then you get n over p elements of the output. And given n rows, 1D partitioning can only use up to n processors because like you can't do more than the number of rows you have. Okay. And then slightly more complicated is 2D partitioning, which is you cut it up, you cut the matrix up into squares rather than just block rows. And there would be at least one element per processor. So now we're doing elements rather than rows. And theoretically, this one could use up to n squared processors because you would just put one element per processor. This is kind of like, we talked about like tiling before. This is basically like tiling. Questions so far? All good? All right, so let's first analyze 1D partitioning. And we're going to do the most simple case, which is that p equals to n. And so the n by n matrix, like I said, you put on p processors, you put one row per processor. And in the beginning, the n by 1 vector is also partitioned in the same way. So you have one element per processor. And that is not what we want because, like I said, everybody needs the entire vector. So we're just going to do an all gather to get the vector on everybody. Like processor 0 has the 0th element of the vector, processor 1 has the first 1th element of the vector, and so on. And if you did all gather, everybody would get all n elements of the vector. So step 1, you use all gather to distribute the vector onto all the processors. That's tau log n plus mu n, which is the thing that I said in the beginning. The message size is 1, this example. And the time, and then step 2 is everybody computes their dot product. Yes. We are going to get the vector entirely on each processor. But like in the initial distribution, there's no repeated data. Like this is repeating the vector n times, one on each processor. So in initial configuration, you're not guaranteed that the data is going to be duplicated. Yeah, because if it was, everybody got one row in the vector, it would just be everybody computes their vector, and then that's it. Everybody computes their one element. Everybody has one element to compute. Oh. This to n is because p equals to n. Like if we go back here, all gather, we're doing all gather, and then it's tau log p plus mu mp, and so m is 1 because m is the thing that m is the amount that every single processor has to send, which is 1 in this case, and then so this just goes away, and then it's just mu p.
So on the side of 1, what are they sending?
They're sending their own vector element. So like processor 0 has the first vector element, processor 1 has the second vector element, and so on. But every processor needs the entire vector.
How did each processor get just one element of the vector?
We didn't count the cost of that, but that's just the initial configuration that we're working with.
Yeah, how did like each processor get exactly one element of the vector, but like an entire row in the configuration?
We didn't. That's not counted in the time. Like step 1 is just when we start at step 1, we're already assuming this configuration. But like, think about like if you're programming this yourself, you have to start on rank 0, and you like would read in the matrix from the file, for example, and then now you have to distribute the matrix onto everyone. So you could do that with a scatter, which we're not counting in the time as well because scatter time is similar to the all gather time. Yeah. So yeah, this is just the configuration that we're working with, and the reason for this is because if you sent out the vector to everyone, I guess that would be similar time. Like you would just broadcast the vector to everyone, and that would kind of be similar time to this all gather as well. Because like say you were broadcasting the vector, which is late then, that would take this time, or that would take this less than this time because it would be mu n log p. But or mu, yeah, mu n log p.
More than that.
Huh?
Mu n log p is mu n log n, right? More than that.
Yeah. Yeah, so that would already count as more than that. So maybe that's why we don't want to broadcast the entire vector everywhere. Yeah. That makes sense? Like, you have to send n elements.
Yeah.
It's going to take you log n levels. Yeah, so that's why you don't broadcast the vector. And then, yeah, so that is the step 1. And step 2, you just do your dot product. That takes time n, and you add them up and you get the total time. And the first one is bigger than the second one, so the time is basically the time of all gather. Make sense? Cool. So in reality, n is usually bigger than p. So if n is bigger than p, then everybody gets n over p rows of matrix A and n over p elements of vector x. And we do a similar thing. Everybody still needs to get the entire vector x. So you do, I'll gather among the p processors, and now the message size is n over p rather than 1. And on each processor, you still do the dot product, but now you have n over p dot products to do rather than 1. So what is the communication time and what is the computation time? Well, the communication time is the time of the all gather, pretty much. And it's going to be, this tau log p doesn't change. Because if you remember, all gather is tau log p plus mu mp. So mu is still mu, m is now n over p, and then p is p. So these two are going to cancel out, and then you get tau log p plus mu n. Okay, the computation time is n squared over p, because you have n over p dot products to do. Each one is going to take you n time. So you just multiply them. And one problem with this is that you can only use up to n over mu processor. You can use order n processors, and notice that n over mu is order n. And the reason that you can do that is for this entire thing to be efficient, this thing needs to dominate the total time. Like the total time if you just added these two up. And if p is greater than n over mu, then you just like divide it in here. So if p is equal to n over mu, this becomes n over mu. Or sorry, that becomes mu n. It becomes mu n, and then that's equal to this. If it's bigger, then that thing becomes smaller, but this thing is still bigger, so you're not getting savings overall. So, you're limited in the number of processors. But it is straightforward to do it this way, so that's one nice thing.
So the computation time is only the local dot product.
Yes.
Why is it like for the communication time? What's the mu n?
This one?
Yeah.
This is because this is the time of all gather. So all gather is tau log p plus mu mp, where m is the message size. And then here the message size is n over p, because everybody gets, in the initial configuration, everybody had n over p of the vector. And then, so the message size is n over
So
p.
n over p, it's sending elements of vector x.
Yes, n over, this is the all gather for vector x. Everybody in the beginning has n over p elements of x. And then, but to do the dot products, everybody needs the entire n elements of vector x. So you do all gather with message size n over p, and then that is m. So mu mp becomes mu n over p times p, and then that's mu n. Yes.
So this assumes that the matrix is already on those processes?
Yes, this is assuming that the matrix is already, like you already have n over p elements on each thing. You could, like when, for example, like think about actually programming this, you would have the entire matrix on rank 0, and then you do a scatter of n over p rows per processor, and then you could say, like, you would know how much that would take you because we have primitives, and then so scatter is this, where m is n squared over p, and that would be bigger than the entire thing, pretty much. So we're just going to ignore that cost because it becomes uninteresting to do the analysis if you count it.
I was gonna say, like, that's hopefully the other ones are not like that, because like what have we been doing when communication time is more than this?
Yeah. So like we start with matrix vector because it's simple, but in reality, like it's not super interesting because the reason is that like the work is not that much compared to the communication time. Like it becomes more worth it to do parallelism when the work is higher than the communication, and we're going to do that because we're going to do matrix matrix. Yeah. So basically, like if the work is linear in the input size, it's going to take you linear to move the data to the processors. So this is just like a warm up. Questions? All right. So we're going to move on to 2D partitioning, which is rather than cutting up the rows, you cut up into blocks. And then the most extreme case of 2D partitioning is if you have n-squared processors. So every processor has one element. And so the n by n matrix is partitioned among this n-squared processors. And like notice that we're thinking about it in like a grid because it's easiest to think about it that way. Like you underneath the grid, there could actually be a hypercube routing the messages, but like it's hard to think about it that way. So think about it as a grid, and each processor has one element, and then the vector x is distributed in the last column of the n processors. So yeah, so every processor is going to need to do just one single multiply add. It's going to need to do like it has one element of the matrix, and then it needs to do it multiply with the relevant vector element. So somehow it's going to have to get the relevant vector element, which conveniently is what is in its row. So one natural thing is like we're going to broadcast a vector element, and then we're going to reduce the results. Okay, so like I said, this is your initial data distribution. Your vector x is just split one element. You have n-squared processors, and your vector x is one element per processor on the last column. So the last column, yeah, the last element has x, but now everybody needs to get x. And then actually what needs to happen is that you need to do this initial configuration where you send, so I misspoke a little bit. Actually, every vector element here, like the column needs it. So like for example, you can think of row 1 and just think of computing like the first element in the upper left. So that's going to need the first element, the upper left element in the matrix, and the first element in the column. And then if you think about the element before that, or one below that, you need whatever's in the processor already, and again, like the first element in the vector. So the entire column is going to need, the entire first column is going to need the first element in the vector. And the entire second column is going to need the second element in the vector, so on. And so one way to do that is like you send this element here to the first upper left, send this element here to the second one, like along the diagonal. And then you broadcast along the column. So now everybody is going to get the vector element that they need. You do your local multiplication, and then you do reduction along your row. Because after this, everybody has the correct matrix and vector element that they need, and then you can just do multiply, and then you got the right output element, but you need to do like reduction because you're doing dot product along the row. And so that is this row-wise reduction, and then in the end, that's it. Yes.
About the initial configuration.
The initial configuration is in the last column of the processors, every processor has the one element of the vector.
Every processor has one element of matrix A as well, right?
Yes, but only the last column has vector x.
Okay.
Yeah. But every processor needs one element of vector x.
Right. Initially, every processor does not have an element of vector x.
Yes, initially only the last column has vector x, and then it's also like top to bottom, because like in the picture that I drew, it's like a square and a thing, but actually it's not exactly what you need, because you need the, like right now it's kind of like distributed along rows, in some sense, but you need it to be distributed along columns, which is fine. You just put it along the diagonal first, and then you do column-wise broadcast.
Is,
Oh,
in-
sorry.
sorry.
You can
In
finish.
all, there are n+1 whole square processors.
Sorry.
There are n+1 square processors.
Oh, you could just put it. You could just put two elements on one processor, because every processor is going to need to hold two elements anyway. So you could just in the last column, you can just hold one element of vector, one element of the matrix and one element of the vector in the initial configuration. Yeah.
Just walk through an example cell, like how does like let's say the second column, third row, how does that contain the dot products of the column and the oh no, this is matrix vector.
Oh yes, yeah. So in the end, you're going to do like the reduction. Let's just say on the last column, and then the last column is going to hold vector y.
Yeah, what was the matrix
No, we're gonna get there, but for now we're just doing matrix vector. Yes.
Just to be clear, where it says n over square root p, that's just like one because there's n for processes.
Yes. Yeah. But like if p was not n, you could also do the same thing. Thanks. All good? Okay. So that is in positioning. And so if you have p equals to n squared, the algorithm is like that. We align the vector along the diagonal, which is 1 to 1, like it just does point send. And so that is tau plus mu. And then we have to broadcast the vector along the column, which is tau plus mu log n. Again, you're just sending one vector element. You do your local multiply, which is just 1 again. And then you sum up horizontally in your row. That is tau plus mu log n plus log n. This log n is for the computation, and then this is the communication. Yes.
So also, is there a broadcast to every processor in the row, which is the same as the column
Is there a broadcast to every processor in the row?
of the one vector element?
No, it's just a point, because you only need it along the diagonal. Yeah. So you get to, but it would, I guess it wouldn't change the big O. But for full efficiency, you can just send it directly. Yes. The initial x vector is stored along the last column. So like the first element is in the upper right, the second element is in one below that, and so on like that. Yeah, because it's not in the right place in the beginning. So you need to send it to the right column that it's going to be in. Because every vector element corresponds to one column in the matrix. So you just send it to the right column, like which is along the diagonal, and then you broadcast along the column. Yes.
To get the partial y values, still we need to across that row.
Yes. Yeah. You're gonna do. This is. It doesn't look parallel, but it's the this is like the computation of the reduction kind of, and then in the end, the output vector y is going to be one element on each of the. Let's say the reduction root was the last processor in the row, then the results would be here. But like you could put the results here or anywhere you want. Like you just specify the root of your reduction. Yeah, so you have to do the alignment, then you broadcast, you do your one single multiplication, and then you do a reduction. And that's it. Okay, the communication time, you add up the communication steps, that's tau log n plus mu log n, then the computation time is log n. That's just from the reduction. Is it efficient? You're shaking your head, no. Yeah, exactly. Okay. Yes, because you have n squared processes and you have n squared work, so you got to do like 1 per, but this is log n. So, yeah, so it's no good to use n squared processes, but it's okay because in reality, you don't have n squared processes anyway. Okay. Yes.
I didn't understand the log in the last. Let's log in.
Is
I
plus login?
understand, like, yeah, you mean login is the thing, is the
Uh-huh.
communication of network, like, login.
Oh, that's just coming from actually doing the additions in the reduction. Like on each, when you do the, like the reduction is a tree, and on each node of the tree, you have to do plus. Yeah, so that's where the, yeah, I guess so, like starting from the top. Actually, there are, n reductions in the last level? Like the bottom level, you have n over 2 reductions. But I guess this is the parallel computation time. Like you do in parallel all the additions, but it's going to be at least one per level, and there's log n levels.
So yeah, I get that there's reduction for getting each y value, but at the end of the we'll see at the end of you gather.
No, it can end up one per. Like if you were actually trying to, if you needed to gather them all in one, like on rank 0, for example, then you would need to gather. But here we can just leave it at one per at the end. Yeah, I guess it depends on like what you're using it for. Like for example, if you're doing another round of matrix vector, like often you do iterative matrix vector multiplications, and so like there's no need to gather them all into one again. Like you're just going to do the same thing again. Now you have the initial configuration again. That's kind of why like the initial configuration was like that with every element one by one like that, because like y becomes x in the next round. Good question. Does everybody see the issue? Like it's you're doing log n. The computation time is log n, but you have n squared processors, so the time is actually like you multiply them together to get the work. Okay, and to fix that, well, p is less than n squared in most cases. So instead, let's say you have p processors, so you cut the blocks n over root p by n over root p, and one because like your processors are in a grid, and let's say you just have root p on each side. And then the vector is also distributed similarly. You have n over root p elements in the last processor column. It's like the same, but now rather than one, you have n over root p in every dimension, like matrix vector. Okay. And then in that case, the analysis is exactly the same, except that the message size would change. And also the reduction. Yeah. So the message size changes for the alignment, the broadcast, and the reduction. They all become n over root p due to the initial partitioning. And so the computation time for each product, now you do this square thing, and that's n over root p quantity squared with your vector of n over root p. And like for parallel algorithms, usually like you run the serial algorithm on every processor. That's kind of like the base case. Okay. So the 4 steps are exactly the same as before. You have to do the initial alignment of the vector along the diagonal. You broadcast the vector elements to the processors along the column, local multiplication, and then you do your reduction along every row. And the only change is now this used to be like 1, now it becomes n over root p. Okay. So we're going to do the same thing. You sum up for the communication time, you sum up like the alignment, the broadcast, and the reduction part. That is tau log root p, because now it's not p in the row of processors, it's root p. And then that's mu times n over root p, which is the message size, times log root p, which is, again, you have root p in every row of your processors. And then computation time now becomes n squared over p, because that's how which took you to do the local reduction, or the local computation. And then, yeah. And that's efficient up to n squared over log squared n processors. And the same reasoning is like, you compare the computation time and the communication time, and you want the computation time to dominate. So that's like the maximum p that you could get. And that is better than 1D, because if you remember in 1D, we could only use up to n, but now you can use up to like something like n squared. It's like n squared over log squared, but it's better.
the last one?
This part? Because you compare, so like the total time is the computation time plus the communication time. And you want the total time to be dominated by the computation time. And so that this thing is getting smaller as p is getting bigger. And so you're saying like, when does this thing cross over with this thing?
So how is that when, like, basically this term would be like log squared n, right? When it's just n squared over log squared n processors. So how is log squared n crossing over?
Because if you put this,
Oh.
if you substitute this for p here as well, like p is equal here and here. So you're kind of like, it's kind of like if you set them equal and then you solve for p. That's like that's the point at which they even out. And you have, I mean, you don't really have like control over p, but you can make arguments about p. Everybody okay on this part? Cool. Yeah, so now we're going to do matrix matrix. And matrix matrix is like, it's like many matrix vectors. All right, so matrix vectors, we spent a long time in the beginning doing matrix matrix. So we have matrix C is matrix A times matrix B, and the serial complexity is n cubed, because every element in C is one dot product of a row of A and a column of B, which is going to take you n work, and you have n squared output elements, so that's n cubed work. And this is like the most easiest way to implement it. You have 3 loops, I, j, and k, and then you just, k is in here, the fast moving dimension, and then you just, like here it's sum, but you could just directly add it up into Cij. People remember how to do this? Okay. Okay, so let's say we have some initial algorithm, and assuming that we have some n squared processors, and every processor ij has, every processor ij is going to be responsible for computing Cij. So it's going to need the relevant row of A, and it's going to need the relevant row of B. Or, sorry, relevant row of A, relevant column of B. It's going to do a dot product. So to compute Cij, you need the ith row of A and the jth row of B for doing notation. And one idea is, so we have some initial distribution of the data, like we did previously, and it's not like not everybody has all the data initially. Let's say you just, yes.
Should that be the jth column?
Yes, thank you. I'll fix it. It should be the jth column. Yes. And yeah, so let's just say in the beginning that we have a similar distribution like we had in the matrix vector case, where every entry, like we have n squared processors, so every processor ij has aij and bij. But you need the column of b and you need the row of I. So you could, but everybody, if you gathered the entire row onto you and you gather the entire column that you're in onto you, that would be enough. So you all gather, this should also say column, but we're going to fix it. You all gather the entire row onto you, you all gather the entire column onto you, and you do your dot product, and that's it. That makes sense? This is like, it's pretty much like the same algorithm that we had for 2D matrix vector, except now you have row and column rather than just the vector. Okay. So consider what data that we needed. So that was fine, except the problem is that the data is much bigger than it needs to be, because now everybody has one whole row and one whole column of the entire matrix. Yes.
Like, there are 2 points, right? The idea is like all gather I throw of A into each processor and B throw.
Yes. Sorry, bth column. Please. Yes.
So my question is like, here there are, so here, what is represented by red and purple as 2 matrices are the same set of n squared. What are 2 n squared?
Yes, you have n squared processors. And in the beginning, processor ij has aij, bij, cij. But however, you need all of ai and you need all of b star j. So you're gonna just all gather within your row, and you're gonna all gather within your column. Then everybody has the right row and column, and you can just. But the problem is that everybody now has one whole row and one whole column, which is too much space because like you had n squared processors, and now everybody has n elements, order n elements. You have one row and one column, and that's n cubed space. But in the initial configuration, it was just n squared space. So that's not going to really work. Yeah. Okay, so we multiply this n-by-n matrix, get n cubed, and we maintain the n cubed complexity. Like we're still just doing n cubed multiply adds. So that is good. Yeah, and then we can block them as well, like we did for tiling. But now, rather than tiling for caches, we're tiling for processors.
So I have a question. Like the previous one, is it that we are assuming X is larger
We're assuming that we have n squared processors.
than process? So why? So isn't like each row, like each processor, they just need one row?
Yes. Because we have n squared processors, and one row is length n, and one column is length n. So every processor has n data.
Yeah.
So that's n squared processors, and each one has n data, so that's n cubed. You can fix it slightly by if you do blocks, like you do blocks rather than single elements per processor. You just need to have less blow up because like every processor has more than one row and column, but it's not so repeated. In reality, like p is less than n squared, so you have to do blocks anyway. Like if you use n squared, you put one element per processor, which does not really work in reality. You have to put several elements per processor.
So this would be tiling.
This is like tiling, yeah. Yes. I think in a previous iteration of this class, they didn't do caching, so they never got to tiling until here. But yes.
Is that the same thing as the 2D partitioning, or is this a separate thing?
No, this is 2D partitioning. Yeah. It's called like tiling when it's on like one processor, and it's called 2D partitioning when it's on multiple processors. But it's the same idea, like you cut the matrix into submatrices.
I felt like Strassen's method is basically just
Strassen's method gets less than n cubed operations. It gets n to the log 2 to the 7.
They did it by just tiling.
It can, like, it is usually formulated as divide and conquer because it does like the submatrix additions and multiplications.
Yeah.
But it doesn't have to be. Like, you could theoretically implement that iteratively. It would be a bit weird, but you could, I guess. Like anything recursive, you can implement iteratively, and vice versa. But it's just like weirder to think about usually in one direction.
What was the main idea behind Strassen's method?
Strassen's method is like, so in the regular method, even with divide and conquer for n cubed, you cut your matrix into 4, and you do 8 submatrix multiplications, which is like 1 for each quadrant, or you do 2 for each quadrant. It's like each quadrant is the sum of 2 submatrix multiplications, and so you have 8 of them because you have 4 quadrants. And in Strassen's, they figured out how to do 7 submatrix multiplications. So the fan out is 7 in the recursion tree rather than 8. And so like in the end, this becomes n to the log 7 rather than n to the log. It's like n to the log base 2 of 7 rather than n to the log base 2 of 8, which is 3. So it's like asymptotically better, but in reality, the constants are higher, so it takes a while. Like it only works for like larger input sizes. But for now, we're just going to consider the n cubed version. It gives rise to nice distributed algorithms. And then we're going to focus on blocking, like tiling. It's called 2D partitioning in this case. Okay, so we're going to do blocks, and consider we have two n by n matrices, A and B, and it's partitioned the natural way, like you have p processors, so like you have root p in the row processors and root p in the column processors, and then it gets the initial configured matrices, but now it gets n over root p squared elements per matrix, or per processor, so that's n squared over p. And so initially, when we had n squared processors, everybody got aij, bij, cij. But now you're just going to get block aij, bij, cij. And then computing the submatrix requires all of the submatrices. Like the issue is the same. You still need everyone in your row and everyone in your column. But now everyone in your row and column are now blocks rather than single elements. But it's the same issue. And you can still use the same algorithm, which is that you all gather now the blocks along your row, along your column. And now you do local submatrix multiply. Okay, so the two altogether operations is going to do this time tau log root p plus this thing, and n squared over p, which is the message size. That's the size of your submatrix, and times root p, which is along the row or along the column. And then the computation, you have to do root p multiplications of n of this size submatrices, n squared over root p squared. Sorry, n squared over p. So you have this many submatrix multiplies, and you have this many. This is the size of your submatrix is this thing squared, but you have to do cube number of multiplies. So total complexity, computation complexity is n cubed over p. And this is kind of like what we expect naturally. Like we knew that the serial complexity was n cubed, and we know that we have p processors. So the best you can do is speed up of p. And indeed, like there's a p over there. And so if you didn't see this p, we would kind of think that we would have an issue, because what was the point of having processors? But now we have p here. So yeah, we did this analysis, but like you kind of know what it's going to be like. You know that there's going to be a p in the denominator. So it's worth it to do it anyway. And then the total time, you just add it up. Local computation time, communication time. And that's efficient for p is around n squared, using the same thing we did. Like you set computation time equal to communication time, and you wait for them to even out. All good? Yes.
Is the divide and conquer approach better than this? Like if we forget about communication and just give each processor that local submatrix and by the submatrix and then just compute the addition.
Mhm.
Is that better than this?
You would still need to do communication because you need
You need
the entire
addition at
block
the end.
row. Yeah. Like, yeah, like you have one block, and you can, basically you're doing like, look at this picture again, like this. You start, let's say like you started here, or actually here is this thing, but because it's this row and this column, so it's actually this one. But you need, like the initial configuration, you have this block and you have this block. But you need all of these and all of those. So you're going to have to do some kind of communication.
So the difference between what we have like today and like versus what we did before with the caching. It's like the caching is shared memory and this is distributed.
Yeah. So in the caching, like you didn't need to do. You can kind of think of like the cache misses as communication, but on one processor, and this is communication across processors.
Does it really always need to have a row column? One block, one block.
Could you say more about it?
So you have one block of one row and one block of one column.
Mhm.
Multiply those.
I see. So like, but so for example, here in this example, there's going to need to be 4 submatrix multiplies, and then you're going to reduce them all. Like, who is doing the submatrix multiplies?
Each process. Or I guess,
But each process has its own row and column to do.
oh, okay, that's.
Yeah. But so like, are you saying like multiple processes? Like you could, multiple processes could do like each, like maybe each more than one process, you could do all of these in like submatrix additions in parallel, and then in the end you reduce them. But then everybody has the same issue. So how would you divide it up? I guess.
I guess. Having larger.
Like in this example, I guess you could have, if you had 4 n squared processors, every square would get 4 processors, and then you could do those in parallel and then together. But then you would need even more processors.
Or I guess
You could use larger blocks. Like if one block was like 4 blocks or something.
Yeah.
Like actually, like normally everybody's computing 1 block of Cij, but instead if everybody computed like 4 blocks of Cij, yeah, I guess so. And then you like divide up by 4, and so everybody does the reduction. Is it better? I'm not sure that it's better in the sense that like it may be a constant factor. Like if you only blow up the block size by constant factor, then you just everything is modified by a constant factor. But if you blow up the block size by more than a constant factor, you have to pay for the reduction. Maybe. I don't know. I gotta think about it. But I think it wouldn't maybe help you in the asymptotics if you're using the same high level algorithm, because the whole thing, like if you look at the analysis, like you wouldn't save the computation time. You're always going to get n cubed over p computation, or you should, because it's going to have to be efficient. Sorry, you're always going to have to do n cubed operations, and then you would still have to do these all-gathers because you still need your entire, like the entire row and the entire column, but they just might be bigger all-gathers. And then, but the length might be less. I guess like they would be bigger. Like you can make these bigger, and then you would make the processor length less, but they might just cancel out. Okay. All right. Yeah, any issues? I already said it because I forgot that I put this here. You use n cubed space. Yeah. Or I guess root p space where p is the number of processors. It was n cubed when p equals 10 squared, but root p is still not ideal. And ideally, in the best case, you want the serial memory that you took over p. You don't want to repeat if you can. Okay. All right. So suppose that we have this processor grid. We have 4 by 4, and this is for illustration. We're going to put 1 element on each processor in the beginning. So processor 0, 0 has A0, 0, B0, 0, C0, 0. And we want to come up with an algorithm with the restriction that you only have 1 instance of the elements from A, B, and C across all the processors. And you can note that like the previous algorithm did not satisfy this, obviously, because we had to repeat the rows and the columns. Yeah. And the way this is going to go is that we're going to look at the expressions for computing the dot products. So for C00, it's A00, B00 plus A01, B0, A01, B10, A02, B20. So like the only thing that's changing is the inner dimension. The outer part is always 0. And if we can consider this thing, the next thing over in the same row, but in 1 column over, it's not exactly the same, but some things are shared. Like for example, all the A's are shared between these two expressions. Like this is A03, B03, A02, A02, like that. And in general, this is true for the entire, for every C that you have to compute in the entire row, that they all share the same A. And that we knew that because we all gathered the same row onto each processor in every single row. And then the same idea holds for the columns B. Like every column shares all this, like every column needs the same B elements across the entire column. And we knew that because we all gathered the columns like in the previous iteration. And so the high level idea is that we're going to share elements, like we're going to add some more communication, but we're going to share the elements in the rows and in the columns. Because every row needs only the same elements, and every column needs only the same elements. Does that make sense? Yes. Yes. We're trying to improve the space complexity, and we're not trying to, without blowing up the computation part. And the thing that we're going to take advantage of is that a lot of the expressions reuse the same inputs. Specifically, every row reuses the same row, every column reuses the same column. Yes.
They're all processes.
These are all processes.
They
Yes.
each have their own three.
Yes. Yeah. For now, for illustrating this algorithm, we're just going to think of it like one element per process. But but they could be submatrices as well. It's going to work for submatrices too. Okay. So at a high level, we're going to try to reuse the same things, but this initial configuration is not going to work because, for example, if you look at here, C01, like it needs A01, but it doesn't need B01 ever. If you look at this, because to compute C01, oh, sorry, it doesn't need, no, sorry, this one. The first row is fine, actually. I think. Yes. But like some of them, how do you say this? The initial configuration is not exactly right for all of them because they do not, like with this initial step, not all of them hold like, some of them hold elements that they don't need to compute their dot product. This one does, it happens to. Yeah, but it doesn't need A01. Sorry, I got confused for a second. It does not need A01 because we have this thing. And A01 never shows up. Oh, A01 actually it does. The first row is fine. Sorry, this first row is fine, but the later rows are not fine. Yes.
I'm kind of confused. Like, doesn't every process like need its like isn't the whole point of a matrix multiplication is the Cij is like the column, the row I and then column J.
Yes.
So everyone
Sorry.
needs its own.
I said it wrong. Everybody needs the entire row and the entire column, but the configuration for doing the multiplications is not right in the beginning. In that you're not multiplying A01 with B01. Yes, sorry. You need everything in your row and you need everything in your column, but you also need the right stuff to multiply at the same time on the same process. Yeah, sorry. Sorry, that was confusing. Also got confused for a second, but that is right. You need the entire row, you need your entire column, but you also need the right things to be in the right place at the right time. And they are not all, like A00 happens to be correct, but like this one is not because the inner dimensions need to match up. So this would need to be like A00 and B01 on the same process at the same time. Yeah, sorry about that. Does that make sense?
So these are not the final places that every single row or column.
No. So this is just the initial setup, but we're going to have to do some rotation to make sure that the correct operands are in the right place for an initial step.
I have a question, like why is it like we read in every single thing on one processor, right? And then later on, is it like we do a scatter it to other processors, and then we do an all gather? Like that seems to be efficient, more efficient than, I don't know, just actually I don't know is that like the only way to distribute data?
Like with scatter, you mean?
Like we essentially do a scatter and then an all gather, right?
We're not going to do an all gather here. Like to get this configuration, you need to do like if everybody started on rank 0, you would need to do scatter to get all the elements onto the different processors. But we're no longer going to reduce. We're no longer going to do all gather within the row or the column because that was the issue with repeating the data. Like because everybody did all gather, then everybody got the entire row and the entire column. But we're going to try to split up the elements in the row and the column and reuse them using communication. That's the high level direction. But first to do that, like to be able to do that, we need to have overlap in the operands in like the stuff in the same row and the same column. But this is not going to work to start with because it's not just like they share the operands, which is true, but the inner dimension needs to match up to do the correct multiply. So we have to change this initial. We have to change the initial configuration such that everybody starts with a correct thing that they need to compute, and then when you do some rotation in the next round, everybody gets an additional correct thing that they need to compute. And they're going to go in like n rounds. Yes. Yes. Yeah. Right now the correct things are the diagonal, and we need to fix that. And we're going to fix that with some initial rotation. Okay. Yeah. So, and the goal is everybody needs to compute one of their multiply adds in each round. And once n rounds have happened, then they have finished the entire dot product. And yeah, it's not immediately right because these are some correct elements, but they didn't line up. And the main insight here also is that you don't have to compute the terms in order. So, because if they computed them in order, like these two would need A00. So we would need to repeat them. But actually, for example, this one can compute A00. Like in the same parallel step, 00 can compute A00, B00, and then 01 can compute this one. So like you can think of like every row has they're like one off, and then they're just computing it around like that. Okay. So to do the initial configuration right, in this example, like we would need B11 up there. So we just ask this one to send up B11. And then we do a cyclic shift along the column like that. Okay. So now C01 needs to, if we send up B11, then it would have the correct A and it would have the correct B. Because the inner products, the inner dimensions match up. And also notice that if we send up B11 here, then you get B21 up there. Like everybody sends their B up by 1 in the column. So then B11 would show up here, B21 would show up here. But now this is not right because you would need A12. You have like B21 and then the inner one has to match up. So this is called Cannon's algorithm. And this is like the classic algorithm for matrix matrix multiply. And the way it works is that so just look at the first row and the first column for a second. We didn't need to fix anything because it was already correct here, like A00 and B00. So let's say we had 4 blocks or 4 elements, red, blue, green, yellow. These are also red, blue, green, yellow. And so in the first step, we multiply the 2 red ones together. And they're correct because they lined up in the inner dimension. And we're trying to compute purple, by the way. And so in each round, this one is going to shift horizontally, and this one is going to shift vertically, so that you get the right colors to line up. Like in the next round, we're good. Just consider processor 00. We compute the red block in the beginning, and in the next round, we're going to need blue because we have already computed red, so we can give it away. So in the next step, blue gets passed left by 1 here, and blue gets passed up by 1 there. So now, the same process, now we have blue and blue. And we can do the multiplication. And same again for green. This one passes left, this one passes up. And again for yellow. and that's 4 rounds, and we had 4 elements, and that's it. This is done. And I guess like the hardest part to think about is that everybody is doing this. Like we just looked at it for one, but everybody is passing their block in the row left, and everybody is passing their block in the row, in the column up. So that's how we got them to line up. And so, yeah, that's how we got them to line up, because if the initial lineup is correct, in the sense that like if everybody has like the same color in some sense in the first in the initial configuration, and they may be different colors for everyone. Like for example, you don't have to start with red, and in fact, other processors will not start with red. Like in the beginning, this processor started with blue, but that is fine because we would also guarantee that in this thing, this would start with blue. So you just need to guarantee that everybody starts with the correctly aligned inner dimension, and then once you pass up and pass left, then everybody continues to have the correct inner dimension. Okay. And then in the initialization, like I said, you just need to rotate. So here, let's consider processor P01. The first row is already fine, but the second row is not fine. Like here, this is processor P01, so we started with blue, but here it has red, which is not right. So it needs to get blue. So we just need to we need to rotate this entire thing 1 up. So you shift the entire column up by 1. And in general, for the jth column, you shift up by j. Yeah. And then again, an example in processor 2.1, 2.1, it has blue, which is not correct because we need to shift this left by 2. Well, this we know we definitely need to shift this up by 1 because it was in column 1. But we're going to shift the rows left by I, where I is the number of rows, or I is the row index. And then if we shift that correctly, then this will get yellow. Like yellow will move 2 over here. And then you shift this up by 1, yellow will move 1 up over here, which is this. And this, which are the same. Yes.
So the initial transpose.
In the initial configuration, you want every column of B to be shifted up by 1. Or, sorry, in the initial configuration, you want every column of B to be shifted up by J, where J is the column. The transpose swaps I and J. The row is not changing, just the column is changing. Or like, sorry, for the initial alignment of the column is changing, and for the initial alignment of the row is changing, and it may change, like, for example, in this one, like 2.1, both the row and the column changed, but A and B were changed by different things. Like, A was shifted left, and B was shifted up.
When you're saying you're shifting it up by J, sending it directly to that?
Yes. You can send it. You can do the shift by everybody sends it, because everybody's shifting up. So like, for example, this one, like, let's say you're just shifting up by 1, like this one would send here, this one would send here, this one would send here. But if you're shifting up by 2, like you could just, this one would send 2 over, this one would send 2 up. So everybody would do like point to point, but however distance they needed. Yes.
I still don't understand why. Like, if I have initially, if I shift the A by 2, still have to shift.
Yes, but for example, here we're looking at 2.1. They're not matching. Like this is blue and this is green.
Oh, so sort of for the initial syntax that we shifted by different amounts.
Yes, exactly. Yeah. So this shifting by multiple things is only in the initial configuration to get the correct inner dimensions to line up. After that, when we actually run the algorithm, everybody shifts by 1 every time. And the reasoning is like once you have lined up the inner dimensions, like the row dimension, the inner dimension is going to move up by 1. The column dimension, the left dimension, the inner dimension is going to move up by 1, and so they continue to align. Yes.
So in this configuration align, that like the first row is all computed all at once, or like each row is computed all at once.
Every square needs n rotations. Once you have done the initial configuration, every row needs n rotation. Like every round is like 1 shift and 1 multiply.
Right. Sorry. Okay, here's my question. So, like, we start with this red, blue, green, yellow on each row, right?
Mhm.
And so originally it would be that the greens would line up on like 2, 2.
Uh-huh.
But we don't want that. We're shifting it such that like the entire like top row lines up, or like every row lines up, as opposed to like diagonal. So it's
Yeah, like the diagonal will, because in the beginning the diagonal lined up, but the rest of them didn't line up. But we want everybody to line up, including the diagonal. Yeah, so the diagonal is still going to line up, but just not in the initial elements that it had. Yeah. So the example, like we started with this. We started with 2, 1, and we have the green in the row and the yellow in the column, and neither of them are correct. So first, we're going to rotate this one. So remember, like this started with blue, and now we rotate that by 2, by 1. Sorry, because we're doing the column. So, oh yeah, we're doing the row. Okay, so this row shifts over by 1 that way. So now blue was here, and now it's here. And now we need to shift column to put yellow on this one. Sorry, hold on. Yes. Yellow needs to go, the yellow part in the row needs to go here, and the yellow part in the column needs to go here. So that's why you shift the column, the row left by 2, and then so you shift the column up by 1. Yeah, and then it is that way. Yellow is here, and yellow is here. And then you can compute the correct submatrix. And that's, then you added in, you multiplied this yellow A with this yellow B, and you got the correct in C. And now you can see like they are aligned. Like if you shift this one left by 1, you would get red. And if you shift this one up by 1, you also get red. So now you compute red. And if you did it 4 times, you would do all of them. And I think I'm out of time, but we'll finish next time. Thanks.